What is a vector? This is the question that unlocks all of modern artificial intelligence. Not matrix, not eigenvalue vector. The humble, foundational vector. If you have ever trained a neural network, used a recommendation system, or run a search in Google, you have used vectors. Hundreds of millions of them. Every second. This video is part of our Maths Behind AI series on Neural Monk. The goal is always the same: build deep, unshakable intuition first. Formulas come second. No prerequisites. No fear. Let us start from scratch. The simplest definition: a vector is an ordered list of numbers. That is it. But when we give those numbers geometric meaning, that is when things become interesting. Take the vector 3, 2. Start at the origin, the center of the coordinate grid. Move 3 steps right. Move 2 steps up. The arrow you just drew from the origin to that point is your vector. It has exactly two properties: magnitude, which is its length, and direction, which is where it points. Mathematically, the magnitude of the vector 3, 2 is the square root of 3 squared plus 2 squared. That is the square root of 13, which is approximately 3.61. Here is the insight that changes everything. Any piece of data you can imagine can be expressed as a vector. A 28 by 28 pixel image is a 784-dimensional vector, one number per pixel. A word in a language model is a 300-dimensional vector. A patient's medical record is a vector with as many dimensions as there are measurements. Everything in machine learning starts here. Vectors can be written two ways: as a row, or as a column. A row vector places numbers horizontally inside square brackets, 1, 2, 3. A column vector stacks them vertically. In machine learning and linear algebra, the column vector is the standard convention. When someone writes V in bold, they almost always mean a column vector. The notation matters because it determines how we compute things. A row times a column is a dot product, a single number. A column times a row is an outer product, a matrix. The magnitude formula works in any number of dimensions. For a vector with n components, the magnitude, also called the L2 norm or Euclidean norm, is the square root of the sum of all squared components. This generalizes Pythagoras' theorem to n dimensions. A unit vector is a vector with magnitude equal to exactly 1. You create it by dividing every component by the original magnitude. Unit vectors represent pure direction with no size information, and they appear everywhere: in attention, in normalization, in cosine similarity. Vector addition has a beautiful geometric interpretation called the tip-to-tail rule. Take vector v equal to 2, 1. Draw it as an arrow from the origin. Now take vector w equal to 1, 2. Instead of drawing it from the origin, place its tail at the tip of v. The result, the sum v plus w, is the arrow from the very start of v all the way to the very tip of w. In component form it is simply this: add each corresponding number. 2 plus 1 gives 3. 1 plus 2 gives 3. The sum vector is 3, 3. Vector subtraction works by reversing the second vector. The vector v minus w is equivalent to v plus the negative of w. Geometrically, it gives you the arrow pointing from w to v, the direction you would travel to get from w to v. These two operations, addition and subtraction, are literally everywhere in AI. When a neural network updates its weights during training, it computes new weights equals old weights minus learning rate times gradient. That one line is vector subtraction followed by scalar multiplication. Gradient descent is applied vector arithmetic. Scalar multiplication is the operation of stretching, shrinking, or flipping a vector. A scalar is just a regular number, not a vector. When you multiply the vector u by a scalar c, you multiply every single component by c. The direction of the vector stays exactly the same as long as c is positive. Only the magnitude changes. If c is greater than 1, the vector stretches. If c is between 0 and 1, it shrinks. If c is negative, the vector flips to point in exactly the opposite direction and possibly stretches too. A special and important case, multiply any vector by 0 and you get the 0 vector, a vector with magnitude 0 that points nowhere. The concept of a linear combination builds directly on top of this. Take two vectors, scale each by a different scalar, and add them together. The result is a linear combination. The set of all possible linear combinations of a collection of vectors is called the span of those vectors, every point you could reach by scaling and adding. In 2 dimensions, 2 non-parallel vectors span the entire plane. This idea of span is central to understanding what a neural network can and cannot represent. The dot product is arguably the most important operation in all of applied machine learning. Here is the definition. Take two vectors v and w, multiply each pair of corresponding components. Add all the results together. That single number is the dot product. For v equals 3, 4, and w equals 1, 0, 3 times 1 plus 4 times 0 equals 3. The dot product is 3. But the geometric meaning is even more important. The dot product equals the magnitude of v times the magnitude of w times the cosine of the angle between them. And that cosine tells you everything. When two vectors point in the same direction parallel, the cosine is 1, and the dot product is at its maximum positive value. When vectors are perpendicular at exactly 90 degrees, the cosine is 0, and the dot product is 0. When they point in opposite directions, the cosine is -1, and the dot product is at its most negative. In a neural network, every single neuron computes a dot product between its weight vector and the input vector. That result is the neuron's activation. In transformer models, the attention score between two tokens is the dot product of their query and key vectors. In search systems, relevance is cosine similarity, which is the dot product of unit vectors. The dot product is the engine of modern AI. How do we measure the size of a vector? There are several ways, and each one matters in machine learning. The most common is the L2 norm, also called the Euclidean norm. It is the square root of the sum of all squared components. For a two-dimensional vector, it is exactly the Pythagorean theorem. For an n-dimensional vector, it is the same formula extended. The L1 norm adds the absolute values of all components without squaring. It measures the total Manhattan distance, the distance you would travel on a grid. The L1 norm appears in lasso regression and in sparse neural networks because minimizing the L1 norm tends to push small weights all the way to 0. The L-infinity norm is simply the largest absolute component. It is useful in optimization bounds and robustness analysis. And then there is the unit vector, perhaps the most useful concept of all. A unit vector has magnitude exactly 1. You create 1 by dividing every component by the original magnitude. Unit vectors represent pure direction, they discard size completely. Why does this matter? Cosine similarity used in every word embedding, every search system, every retrieval augmented generation pipeline computes the dot product of two unit vectors. So when you call cosine similarity, you are normalizing both vectors to unit length first, and then dotting them. That is it. That is the whole operation. Let us make this completely concrete. What does a vector actually look like inside a machine learning system? The input to any neural network is a feature vector. For a patient prediction model, it might be age, BMI, blood pressure, glucose level. Each measurement becomes one component of the vector. That vector is the data point. The weights of one neuron form a weight vector, one weight per input feature. The activation of that neuron is the dot product of the weight vector with the input vector, plus a bias. That is the entire forward computation for one neuron. When we train the network, the gradient tells us how to adjust the weights. The gradient is itself a vector, one partial derivative per weight. The update rule is simple vector subtraction, new weights equals old weights minus learning rate times gradient vector. Word embeddings make this even more vivid. A language model represents every word as a vector in a high-dimensional space, perhaps 12,000 dimensions in a large model. Words with similar meanings cluster nearby. You can do vector arithmetic, take the vector for king, subtract man, add woman, and you arrive at a vector very close to queen. That is not magic. That is what happens when you train vectors to encode meaning through their geometric relationships. Every major breakthrough in AI over the last decade is, at its core, a clever use of vectors. Word2Vec and glove train word embeddings, dense vectors where the geometry encodes semantic meaning. Cosine distance between embedding vectors measures word similarity. The famous analogy arithmetic works because meaning is encoded linearly in vector space. Image recognition uses convolutional neural networks to convert images into feature vectors. Two similar images produce vectors that are close in feature space. Image search, face recognition, and content recommendation all rely on finding the nearest vectors in a massive database. Recommendation systems model users and items as vectors. A predicted rating is the dot product of the user vector and the item vector. Matrix factorization, the technique that powered Netflix's early recommendation engine, is exactly vector arithmetic applied to user-item interaction data. And in transformer architectures, the foundation of GPT, Gemini, Claude, and every modern language model, the attention mechanism works entirely through vectors. Each token becomes a query vector, a key vector, and a value vector. The attention score between two tokens is the dot product of their query and key vectors. The output is a weighted sum of value vectors. The entire architecture is vector operations, end-to-end. Here is the complete picture of everything you now understand about vectors. A vector is an ordered list of numbers. Each number is one dimension. It has magnitude measured by the L2 norm and direction, which is its geometric orientation. Vectors can be added tip to tail by summing components. They can be scaled by multiplying every component by a scalar. A linear combination, scaling and adding multiple vectors, can reach any point in the span of those vectors. The dot product of two vectors is the sum of their component products. Its sign tells you whether they are aligned, perpendicular, or opposing. The dot product divided by the product of magnitudes gives cosine similarity, the universal measure of vector similarity. Unit vectors have magnitude exactly 1 and represent pure direction. Normalization, dividing a vector by its magnitude, is one of the most common operations in machine learning. And putting it all together, in a neural network, every input is a feature vector. Every layer's weights are weight vectors. Every activation is a dot product. Every gradient is a vector. Every update is vector subtraction. Deep learning is applied vector calculus, running on hardware purpose-built for vector arithmetic. Vectors are not just a tool. They are the language of modern intelligence. Next up in our Maths Behind AI series, matrices. If vectors are arrows in space, matrices are the rules that move that space. Subscribe to Neural Monk and we will see you in the next video.